This is the third of 4 lectures on Chapter 14's Survival Analysis chapter of Rossner, and this is going to be an introduction to survival analysis. So this will be an introduction to more classic survival analysis, which includes things like the log rank test statistic, definition of the survival functions, the Kaplan-Meier curve, those kinds of things. Prior to this, what we were focusing in on was the incident rate ratios, the calculation of person time years within the survival analysis realm. So first we want to define the survival function. The survival function S of t basically gives the probability of surviving up to time t for each t greater than or equal to 0. After you define a survival function, the hazard function is the next thing somebody's going to ask you about. So the hazard function ends up being the instantaneous probability of having an event at time t per unit time, or the instantaneous incidence rate given that one has survived up to time t. So in particular, h of t is defined in the following manner, and you look at the incremental change in time. And an example of how you would calculate this is if you were to look at the U.S. life table data from 1986. This is the example in particular. They followed 100,000 men from birth to up until 1986. And you want to look at, you're given information about how many survived to age 61, how many survived to age 80, how many survived to age 81. You would then look at how many men survived up to age 60, which was 80,908. How many men survived at age 61? 34,789. And therefore, if we were to ask somebody, if somebody would ask you about the hazard at age 60, based on this 1986 data, you would be able to calculate the hazard using the hazard function. The hazard at 60 will be the difference between 80,908, 34,789, divided by 80,908, which gets you this 0.017. You could also do that for age 81, and here we see that it is 0.088, and then therefore the interpretation for both of these would be that the 0.07 that we observe for the hazard at 60 is that the probability that one has survived to age 60 but will die within the next year is 0.017. And you could do the same basic interpretation for those at age 80 with the 0.08. So what do we want to get into next is the estimation of survival curves. To estimate the survival probability when the incident rate ratio varies over time, we are left with two basic ways, a parametric survival model or the non-parametric method. So the non-parametric method that we're going to be looking at is the product limit or the Kaplan-Meier estimator. The Kaplan-Meier estimator supposes that individuals in the study population are assessed at particular intervals of time, and in this case we're going to assume that we have k points in time where the times do not have to be equally spaced. The probability of surviving up to time t then is calculated by looking at the probability of surviving up to time 1 times the probability of surviving up to time 2, given that they got to time 1, all the way up to the probability of surviving to time t sub I, given that they survived to up to time t sub I minus 1. So the example that we're going to look at here includes 234 smokers who expressed a willingness to quit smoking and were followed for a year to estimate the cumulative incidence of recidivism. That is that the proportion of smokers who quit for a time but who started smoking again. And so therefore subdividing the study population by those that are greater than 40 versus those that are less than or equal to 40. The data is also will be shown in the following table, but you can get this online or on the CD if you depending on which version of the text that you have, but it's the smoke.dat data. So here it is in table 1. This is the number of days that they quit smoking, and these are broken out by the age group. So we want to estimate the survival curve for people age greater than 40 for the participants depicted in Table 1. So for those that are greater than 40, we see that the survival at 90 is 1 minus 92 divided by 120 at 0.233. Note that 92 people failed to quit at time point 90 days, so the probability of failure at this point is 92 over 120. Then we look at the survival at 180. That's equal to the survival calculation at 90 times 1 minus 4 over 28. That gets us 0.200. If we note that we use the Kaplan-Meier to estimate the survival at 180, we divided the next failure, 4 over 28, because out of the 120, 92 had already failed at the first time point, leaving us with only 28 persons that entered into the next group above it. So in a similar way, we would also get the survival at 270 and survival at 365. Censoring, just so we know the definition of it, occurs when the value of a measurement is only partially known. So a participant has been censored at time t if the participant has been followed up to time t and has not failed. Okay? There's a couple of different types of censoring we can encounter. Right censoring, the most common, meaning that to the right of entry into the study time period. Left censoring, interval censoring, type 1 censoring, and type 2 censoring. Right censored data are data in which a subject is known to have survived for at least t time periods, but the failure time after this point is unknown. So this is very much the common type of censoring that we encounter in most of our data sets. But like, for example, in a clinical trial in which the endpoint is recurrence, a subject may have remained in remission for 13 weeks during the study and did not experience a recurrence as the end of the study. So then the survival time for this subject is denoted by 13 plus weeks because the event happened sometime outside of the study window. Left censoring is a data point is below a certain value, but it is unknown by how much. So something like this is censored. In a study where age of legal blindness amongst subjects with RP, there may be a subset of subjects who are already legally blind at the start of the study, and the precise age in which legal blindness is unknown. It's uncertain. Interval censoring is where a data point is somewhere on an interval between two values. So in a study of age of developing breast cancer amongst postmenopausal women, right, we might know that a woman is breast cancer free at age 50, but has developed breast cancer by age 52. The precise age of diagnosis is unknown, and then the data would be then therefore interval censored. Suppose that we want to look at the Kaplan-Meier, and note this too, the Kaplan-Meier, some people will refer to this also as the product limit. It's an estimator of survival or censored data. The notation we need to pay attention to here is the S sub I minus 1 subjects have survived up to what? T sub I minus 1 and are not censored at T sub I minus 1, of whom S sub I survive, D sub I fail, and I sub I are censored at T sub I. That sounds very tedious, but basically it's the way we figure out what somebody's survival value is if an event has occurred, or D sub I has failed, and I sub I is the indication of whether it was censored or not censored, and T sub I is the time they're contributing to the overall study. The Kaplan-Meier estimator of survival probability at time T sub I is then defined like with the following equation. So if you look at example 14.3, it's presented in the data that you see in table 14.12. It also estimates the survival probabilities. We will show how you get these probabilities using the Kaplan-Meier. If If you look at column 6 in row 1, the calculation you see there is 1 minus 3 over 172, yielding 0.9826. The 3 over 172 is the failure probability at t sub 1. And row sub 2 would be 1 minus 6 divided by 165 of 0.9636. The other rows are then done in the same exact way. So column 7, which is the survival probability estimator, the first row looks a lot like the first row in column 6. It's the 1 minus 3 over 172. However, when we get to the second row, right, and here's the conditioning issue, we look at this 1 minus 6 divided by 165 value, but we buffer it by multiplying it by the survival probability that was present in the interval just before it. So we use the Kaplan-Meier. What we used here, the Kaplan-Meier survival probability estimator, which we defined above. Column 7 can simply be obtained by multiplying the sequential probabilities of column 6. So the estimation of the hazard function, using the similar method, the estimated hazard at time t sub I is the hazard at t sub I is equal to d sub I divided by s sub I minus 1. So d sub I is, what was this again? This is the number of participants with events at t sub I, and s sub I minus 1 is the number of participants available at examination at times t sub I. To estimate the hazard at each year of follow-up for each vitamin A dose group based on the data in table 1.12, we would then look at the estimates that are given in column 8. In column 8, we look at the hazard for the first row as 3 over 172, and the hazard in row 2 as 6 over 165, and do all of the other rows the same way. If we want to suppose that the S sub I1 subjects have survived up to T sub I1 and are not censored at time T sub I1, of S of I of whom the S sub I survive, D sub I fail, and I sub I are censored at time T sub I, for all I equaling 1, 2, all the way through K, a two-sided confidence interval, this should be 1 minus alpha C sub I for survival probability, is given by looking at the upper and lower values of that confidence interval and exponentiating both sides of it. So we would calculate C sub 1 and C sub 2 by taking the log of the estimated survival probability at time T sub I and minus the critical value, which is typically 1 minus alpha over 2, the z-score of 1 minus alpha over 2, where alpha is usually 0.05. And we take the standard error of that point estimate. And the standard error of that point estimate is equal to the sum, the square root of the sum of each of the d sub I j's divided by the s sub I j minus 1 times s sub I j minus 1 minus d sub j. So the Kaplan-Meier estimator of survival probability at age 6 is given in table 14.12. To obtain a 95% confidence interval for the survival probability at 6 years for the patient assigned to that vitamin A group of 15,000 units IUs a day, we would look at S of 6, which equals 0.502 that we calculated from the table. And we would take the log of this, which gets us minus 0.5975. And the standard error of this, which is again, the sum of each of these d sub I, the survivals times the difference in survival minus the di. And we would get 0.0823. So therefore, to construct the rest of the confidence interval, we would take the point estimate of interest plus and minus and plus the z critical score times that 0.0823, getting us a lower bound of minus 0.75 and an upper bound of minus 0.43. So the 95% confidence interval for S sub 6 is the exponentiation of both those values, getting us between 0.4682 and 0.6465. Now we move on to the log rank test. The log rank test is used to compare survival curves of two independent samples. This is a very useful test. The log rank test is more powerful as compared to other methods if the incident rate greatly changes over the years. So to compare incident rates for the event between two exposure groups where the incident varies over the period of follow-up, we use follow-up time, the total follow-up time, we use the following. We subdivide T into K smaller time intervals over time over which the incidence is homogeneous. And we compute a 2x2 contingency table that corresponds to each time interval relating to incidence over the time interval to exposure status, either exposed or unexposed. Then we consider censored subjects at a particular time as having a slightly longer follow-up time than subjects who fail at a given time. So therefore we will be paying attention to the following table. The ith table for the ith interval of interest would be, if we look at the following incremental counts within each of these, for those exposed and unexposed, we see marginal totals and an n sub I. N sub I1 then is the number of exposed people who have not yet had the event at the beginning of the ith time interval and were not censored at the beginning of the time interval. If you're looking at N sub I2, you're talking about the number of exposed people who have not yet had the event at the beginning of the ith interval time interval and were not censored at the beginning of the interval. If you look at all the quadrants within that within that 2x2 table, the upper left quadrant is the A sub I is the number of exposed people who had an event during the ith time interval. B would be the number of exposed people who did not have an event during the ith interval. The C and D's then are both are in the numbers within the unexposed people. C's are the ones that had an event during the ith interval, and D are the ones that didn't have the event during the ith interval. So, not a surprise here, we end up effectively calculating what is like a strata-specific chi-square for each of the ith time intervals. And for the overall chi-square, the likelihood ratio, the log rank, the log rank, we're looking at the observed minus the expected with this 0.5 correction factor squared divided by the variability of the log rank. The observed will be the total of all the observed value A sub i's in each of the intervals, and the expected would be the marginal totals divided by the total within this, the cell over all the intervals of time. And the variability is calculated in that manner. For a two-sided test with a significance level of an alpha value of 0.05 typically, we would then compare the chi-square that was obtained, and then the exact p-value for this test would be, the probability of the chi-squares of 1 degree of freedom greater than or equal to the chi-square of this log rank. We are again only using this when the variability of the log rank is greater than or equal to 5. To evaluate then the statistical significance between a possible association between age and the incidence of recidivism that we saw in Table 1, we would then look at we would divide the total time into a small interval and do a 2x2 table for small time intervals given exactly like we saw here. But the incident by age for the 0 to 90 day period would look like the following. For 91 to 180 would look like this. For 181 to 270 would look like this. 271 to 365 would look like this. And what that gets us is, well, all these little mini tables, is a calculation at each value for the observed and the expected, and each component of the sum is the expected value for the first cell. And this is the calculation for the variability of the log rank. And what we end up, and note too that when we do calculate the variability of this log rank, we get 14.829, which again is greater than or equal to 5, so we can use the log rank test appropriately here. And we would get a log rank test statistic of 0.29 when we calculated this thing in total. And if we compare that to the 3.84 critical value we would get with an alpha of 0.05, then we see that that log rank, the test statistic is smaller than the critical value, and we fail to reject the null. That would be equivalent to saying that there is no difference, given this test, we would expect that there is no difference in recidivism rates between younger and older smokers. So that's a brief example of how you would calculate the log ranked statistic, and it concludes the third of 4 lectures on survival analysis.